So now we're going into ideal gases, and this is important in that it's actually a new model. So it's important to realize whenever we're talking about ideal gases, we are making a simplification. One is that we're going to treat all atoms as hard spheres. In some cases, I'm going to use the word atoms. In other cases, I'm going to use the word molecules. In other cases, I'm going to use one slash the other. What's important to recognize here is we are basically saying in this model, one equals the other. So obviously, if you know some chemistry, you know that that's not true. But when we think about our gas, we're going to think of little hard spheres, and we're not going to care whether those hard spheres are made up of a single atom or multiple atoms, all the same thing. The other thing that we're going to think about are elastic collisions, that these are the only interactions. So these can bounce off of each other, as we've learned about before, and then they zoom off in new directions. However, elastic collisions means that energy is conserved. Now in this case, this would be total energy, but we don't have a change in energy overall of our system. Now, another thing is that we don't have any attractive forces. That means that these molecules will go in straight lines, that they only interact when they actually touch each other. And we're going to imagine these molecules in a container, and that there's no attractive forces between these molecules and the walls of the container. Now, this might be something that, again, you know isn't actually true, but it's going to work for our purposes. The last thing is that we're going to say the atoms are small, so we don't have to worry about that there won't be enough space to put however many we want. We're going to always assume that the density is low, there's always a lot of space in between them, and we don't actually have to say what their volume is. So these are things that are not actually true, but are going to be imagined for our ideal gas model. So in the real world, this is fairly valid when the density is low. If you have a really high density gas, this isn't true. And if the temperature is far from the condensation point, so as long as the gas isn't close to being a liquid, these two things are true. Again, not 100% true. However, for the physics we're about to do, this would be valid. We are going to be using the ideal gas law, which is going to be expressed in two forms. The first is that PV equals nRT. P, lower p, stands for pressure here, not momentum. It is a little bit confusing. Capital V will be for volume. Lowercase n is for the number of moles, so be careful about that. Capital R is going to be the universal gas constant, the values given here, and T will be temperature in Kelvin. Now, part of where this ideal gas law is coming from is that if we actually do this experimental measurement for a number of gases, thinking back to our constant volume gas cylinder, that if volume was constant, we saw that pressure was increasing linearly. In that case, N isn't changing because we have a fixed amount of gas, so we saw a linear relationship between pressure and temperature. If we change the volume, we would just get this same line based on either a change in pressure or a change just by overall scaling pressure or temperature. So this is a straight line that we get for every single gas as long as it is modeled accurate or reasonably well by the ideal gas model. And we see that there's this linear relationship. So what we get to do now is express this in slightly different units, but then I'll be talking about what it's actually useful for. Now, if you have encountered this before, such as in chemistry classes, note that our units here are a little bit different. The units for R itself, the ideal gas law, is joules per mole per Kelvin, or, right, this is a temperature increment. And that the units for pressure are pascals, which is the SI unit for pressure, which is newtons per meter squared. And you should be able to think about this because pressure is force divided by area, so newtons divided by meter squared. You don't have to use it in pascals. It's equivalent to say this. So be careful that you don't use liters and atmospheres or whatever chemists choose, because that's not what we use here. A second form, we've changed the units of n and of the constant. Now we have Boltzmann's constant, which is actually just equal to our previous constant, the gas constant, divided by Avogadro's number. And so what that means is we've basically multiplied this previous value by Avogadro's number, right? So this constant or not quite a constant, but the number of moles becomes the number of atoms, or again slash molecules, by being multiplied by Avogadro's number, and K becomes, well, previously R becomes K by dividing by Avogadro's number. So this equation is completely the same, just different units. So be careful when you go to use the ideal gas law. Make sure that you're either talking about the number of atoms slash moles and then using Boltzmann's constant, or you're using the number of moles and using the universal gas constant. So little n goes with R, capital N, atoms, molecules, goes with K. But otherwise, exact same thing, and you don't have to change the units for pressure, volume, or temperature. So how do we actually use this? The idea being that we've just said PV equals, say, nRT or nKT. Notice that when I say n, I can't really differentiate between lowercase or uppercase n. So I can divide T, and if the amount of gas is not changing, N and R is equal to capital N times K, and these are both equal to a constant. So PV over T, while these three are variables that are changing based on the state of the gas, these equal a constant. This means that we can relate two different states of the same gas. So if it's in an initial state described by a pressure, a volume, and a temperature, that equals this or this, which they're both just constants. And if you then transform the gas by having it undergo some sort of process, which we're about to talk about, you then get a new pressure, a new volume, and a new temperature. But note that what this actually means is that your initial state equals your final state as long as you express them in that form. If you know everything about your initial state and you know two of the variables describing your final state, you can then calculate the third. You can also actually do some proportionality. You can actually relate your initial pressure and volume to your final pressure and volume, and then say proportionally how your pressure itself, how your temperature has changed. So if you know these values, even how they've changed as a ratio, that will allow you to figure out how your temperatures have changed as a ratio. So that's something really helpful.